Okay, all you, Andrew.
All right, thanks, Chris. Give me just 2 seconds here. Get my ducks in a row. Okay, hello everybody. As Chris said, my name is Andrew, and today I'm going to show you guys a live demonstration of performing polarization resistance or linear polarization resistance, LPR, and EIS for calculating corrosion rates. There are 2 different techniques, but at the end of the day, the actual experiment isn't too different from one another. Both of them involve making a small perturbation relative to the open circuit potential and monitoring the current. But at the end of the day, it's 2 different experiments, and hopefully we can converge on a similar result for polarization resistance. Yesterday I ran quite a few of these, and everything was running well, and wouldn't you know it, it's a live demo, and the last 2 experiments I ran gave me somewhat concerning results, but that's the nature of science. So I'm running open circuit potential on the cell we're running right now, and I'm going to let that keep on going for a while here while I talk about the 2 techniques. But basically what we're going to do, we'll do a quick little summary of what the 2 techniques are, and then also talk about how we're going to take the data we get from the experiments and figure out what the polarization resistance is, what the corrosion the corrosion current, the I core, the corrosion related to the current you would see during the open circuit potential, and then how we're going to calculate the actual corrosion rate from those 3 different values. So first we're going to find the polarization resistance, then we're going to find the corrosion current, I core as we'll refer to it, and then we're going to find the corrosion rate. And we'll show you how we calculate those things. So polarization resistance or linear polarization resistance is the first technique we're going to do, and it would be known as an active technique. We're not just monitoring the system, but we're going to actively perturb the system to gauge a response out of it. But even though it's an active technique, it's considered non-destructive. We could apply much higher potentials to get higher currents that would be considered more destructive. So it's kind of a balance. It's an active technique, but non-destructive. Same with EIS. You could describe it the same as well. It is a very fast and simple experiment to perform. The devil's always in the details, and the devil might pop up today. We'll wait and see. But compared to traditional weight loss experiments, we're just orders and orders of magnitude faster, and it's a good first step in figuring out what the corrosion rate of your material is, comparing different materials, see which one's going to perform better. You can get answers to those questions much faster than more traditional weight loss. Just do a mass measurement at the beginning, drop it into a corrosive environment, wait a few weeks, a few months, and then pull it out and see how much mass has been lost. It's kind of the tried and true method, but we're going to do this in about maybe 5 minutes to run one of the experiments. So 10 minutes in total to run both. But there's a couple things that you're going to need. One, for both experiments, you need a stable open circuit potential. If your system is unstable, then the data is not going to be reliable. It's going to look horrible too. In the name, linear polarization resistance, the data we hope to be linear or pseudo-linear. If it's not, then the data is no good, and that likely can be pointed to having an unstable open circuit potential. There are other culprits, but that's probably always the first thing to take a look at. And that's the first thing you do in this experiment is just monitor OCP for a while, make sure it's very stable. That could happen in a matter of minutes. That could take hours, days, weeks, depends on your particular system. And then we're going to scan over a very small potential window, about 10 millivolts, on either side of the open circuit, the anodic and cathodic direction. And The reason that we're just scanning a few millivolts in either side is so that the system and the response remains essentially linear. Electrochemical systems are highly nonlinear systems, but if you stay close in this range, then you can get a linear response that makes the data analysis and the math much, much simpler. And essentially, what we're going to do is make a slope of voltage versus current, and we're going to make a graph of voltage versus current, and the slope of that is going to be the polarization resistance. Simply applying Ohm's law, V equals IR, or it's going to be the slope. So for this experiment, we're going to monitor OCP, allow it to stabilize, which is what I'm doing right now on the cell in the background. We're going to apply a voltage that's anywhere in the range of 10 to 15 millivolts negative of OCP, and then scan slowly, generally like probably about the value I've given there, about 125 or 0.125 millivolts per second. I'm going to do it a little bit faster just so we can get through it a little bit quicker. And then you're going to scan to a final voltage that's about 10, 15 millivolts positive OCP. During that time, we're just going to monitor the current, and hopefully we see a linear response out of it. So we'll go ahead and plot the voltage versus current, as I mentioned before, and then we're going to isolate some of the data and figure out what the slope is of that, and that slope is going to be the polarization resistance. From that value, we can use the Stern-Geary equation to figure out what I-core is. I-core cannot be measured directly. That's why we're using this technique to figure out what that is. And then that corrosion current, we can convert to a corrosion rate. And I'll show you the basic equations we're going to use to do that. So this is the Stern-Geary equation. It's derived from the Butler-Vollmer equation. Don't want to get too much into it, but kind of just show you how it works out. So this is the graph that we would produce, is a graph of voltage versus current. And if we take the differential of this, then we're going to end up with the polarization resistance. And that's going to be equal to the Stern-Geary equation here, where you have BA and BC are the Toffel constants. You can find those from a Toffel curve, and that might be a good demonstration here in the near future. But those you can figure out experimentally. It's possible somebody's already done that work for you, and you can get it from literature, but it's going to change between one material and the other, so I'll be wary of that. So it's just going to be a relationship between RP, the Toffel constants, and I-core. So we're converting the I-core value, the polarization resistance value here to an I-core value by rearranging this equation. And I will say that the area of the electrode has to be taken into account. That's why you see these two different values of the units for RP. So somewhere in here you have to refer to what the area is for the exposed area of the electrode. Once we figure out what I-core is, then if we want to convert that into a corrosion rate of milliinches per year, you would just apply this equation. The equivalent weight is something you'll need to know, and the density, and you can simply convert this I-core to a corrosion rate, and there you go. 3 steps, and you have what your corrosion rate will be of that particular material exposed to that specific electrolyte. And yeah, there you go. You'd have your corrosion rate. Simple as that. The other technique, EIS, what we do there is apply a small perturbation, an AC signal relative again to the OCP, and we're going to then monitor the resulting current and the phase angle through the cell. We're just going to apply, again, a very small signal relative to OCP, about 10 millivolts. Again, so that the response is pseudo-linear. That's going to make the math easier once again, because we are going to be in a linear region instead of dealing with a non-linear response. And essentially what we're going to do is apply voltage here, sine wave, and then measure the magnitude of the resulting current, and then the shift and phase angle of that. We'll record both of those. You can present those in either a Bode or a Nyquids plot. We'll take a look at both of those. And then from those resulting plots, we can then use equivalent circuit modeling. For the system I have, a modified Randall cell such as this, where I'm going to use a constant phase element as opposed to a capacitor, just because the fit's probably going to be a little bit better to model what the system is. I'm not really concerned with this value or this value for this experiment. This RU is the uncompensated resistance, the solution resistance in the system, but I'm concerned about what value I'm going to get here for RP. Another way we can look at this is the Nyquids plot, and if we get a nice semicircle, we can measure what the diameter of that semicircle is on the x-axis, and that should be equal to RP or very, very close to it. So a couple different ways we can get to that value. And once we have RP, we go right back to doing the same thing that we did right back here, where we have our RP value. We're going to convert it to find I-core, and then we're going to take I-core, we're going to convert it to a corrosion rate of milliinches per year, and we'll see what the two values come out to be. So let me get off PowerPoint, and first I'm going to show you the cell setup right here. Now you should be able to see my camera, I believe, and somebody let me know if you're not looking at my camera right now, but I believe you are. Essentially, this is what we're going to take the measurement on. Piece of stainless steel right here. I'm going to use the pink test cell, which I have right here. This isn't the cell I'm actually going to use. I have that running over here on the side, getting stabilized and conditioned for experiment that we're running, but I at least want to show you how I'm setting up the cell. So stainless steel is going to sit right here on the top of the plate. I have my sample mask. Let me open this up so you can see the whole. So here's the sample mask with the exposed area right there. I'm going to take that, put that right down here on the surface, like so, and then I'm going to make sure I have good adhesion, particularly around the exposed area, because you don't want bleeding underneath the mask. So have that. So and then I have this little O-ring and this cylinder. Such, I'm just going to set that right on top. Put this on top of the O-ring. Then I have my clamp that's going to clamp everything together. Slide that in. Such. And I can squeeze down the clamp, and now it's one. It's put together. So this is my working electrode right here. It's my sample. That's the exposed area of the working electrode. And I have my counter electrode right here. It's just a graphite rod. I have my reference electrode right here. This one is actually a silver chloride, but in the cell I'm using, I have a calomel reference electrode. This sits in the top. You would fill this up with solution up to the point. Let's see. I don't know if you see all these notifications popping up in my video, but either way. You would fill this up with your solution. Make sure you have your reference and your counter submerged in the solution, and essentially you have your 3 electrode cell, much like what I have connected and running right here. Let me turn off my open circuit potential measurement just briefly. I'll go ahead and show you what I'm doing here. So I've been running this OCP measurement here, what was that? Just about since I started speaking with you. Let's see, this is coming my way. So in the roughly, what has that been? Well, I can't do the conversion for that many seconds, but it's probably been about 20 minutes now. We've gone from about 400, negative 476 down to about 42. Not much of a shift. This might seem like it's unstable just because of the scale, but relatively speaking, it's pretty stable. Like I said, I had to just replace and put a new piece of steel in there, so it's probably trying to work everything out and become equilibrated, but I think we'll still be able to get a good measurement out of it. But I'm going to stop this measurement for right now so I can disconnect the cell and show you guys I didn't want to do that while it was taking the measurement. But here is the cell that we're running. Let me show you my screen again. Okay. This right here is the cell that we're going to perform the experiment with. You can probably see it has solution right in there. You have about 0.1 molar sulfuric acid in there. It's another reason that I wanted to put together that other cell for you to see. I didn't want to have to put this together and pour acid in it and all that kind of stuff sitting here at the desk. Try to maintain some degree of safety. So in terms of connections, for our cables, this white plug or white lead will accept the plug for the reference electrode. You have your green current carrying cable that you're going to connect to your working electrode, which is going to be the sample. Same with your working sense cable. That's also going to be connected here to our working electrode, which is our sample. And then we only have left the red counter electrode, which I'm going to connect here to the graphite rod. Let's make sure nothing moves here. I have one of the Gamry interface 10 pens that I'm going to use for this measurement. Move that to the side. And that's the basic setup here of the cell. Let me recall these on as I'm moving everything. All right. Let me adjust a few things. Mind. Okay, let's go back to framework. Framework is where we run our experiments from. I believe everybody should see the Gamry framework screen right here. It shows the potentiostat right here that we're connected to. And we're going to run experiments. Polarization resistance right here. I've been running these, so I'm able to access these right here. They're actually part of the DC corrosion package, which is polarization resistance. The other one is EIS, which is in the electrochemical impedance. It's potentiostatic EIS. But first, we're going to run polarization resistance. Let's change this to number 5. So here's our setup screen. What we're going to do is run our scan from an initial to a final voltage. Like I said, I'm going to do this about 15 millivolts either side of open circuit. That's why this is versus open circuit. So we're going to start from negative 15 millivolts versus open circuit and scan to positive 15 millivolts versus open circuit. And I kicked up the scan rate to about 167. In the slide previously, it showed 0.125, but I'm just speeding it up a little bit. We're going to take a sample every second. The sample area I have is 1 centimeter squared. For the density and the equivalent weight, I'm just going to use our default values here. They're pretty close to steel. They're not exactly what they need to be, but for a demonstration purpose, it's perfectly fine. Same thing with the TOEFL constants, 0.12. These generally are going to range for the anodic one, about 0.1 to 0.12. Cathodic could be 0.1 all the way to infinity. These two values, at least for now, are going to be fine. Even a little variation in these really aren't going to affect the result too terribly much. So to use the default values are going to work perfectly fine for our demonstration. And then right here, the initial delay you see here, it's going to measure my open circuit potential. I have it set for 10 seconds. And there's also stability right here. So if you wanted to measure it for a much longer amount of time, let's say you wanted to do it for an hour, but you became stable within 1 millivolt change per second, then before that 3600 seconds is up, if it reaches the stability, it's going to go ahead to the next step of the experiment. That's a useful feature if you have our instruments that you may or may not know about. But those are all the setup parameters right here for the experiment. So we're going to go ahead and start, and let's see what kind of results we get. First, it's going to be measuring the open circuit potential. So that's what you see right here. We're sitting just about at negative 486 millivolts. You can do that for 10 seconds. We don't see much of a shift, so that's pretty good. And now we are actually collecting data. So let's see what happens. First couple data points actually ended up in the direction you wouldn't anticipate initially, but as we move closer to that open circuit potential and move closer to zero amps of current, then we should maintain linearity for the most part.
Andrew, can I jump in here while this is running now? Okay, so we had a couple of questions. I thought this is a good time now that the scan is actually
I was just about to say that, yep.
So one of the first questions was about the mask that you put on the metal sample. Is it necessary to put masking, that sample mask on the metal?
Is it necessary? No, it's highly recommended. There's so many variables in this system. To control them all is very, very difficult. So anything you do to help yourself out is probably a good plan. So by using the mask, there's a couple things that you're doing. One, you're defining your surface area to a designated size. So that's going to help you out in your calculations. The other thing is that O-ring, that curvature, as it meets your sample, can kind of skew what your results are going to be. You can have something called edge effects. So by using the sample mask, you avoid that curvature of the circular O-ring meeting the flat surface and that crevice that's formed right there. So that's another big reason to use the sample mask. But again, I could have run this without the sample mask. Data might have looked good, it might not have, but it's kind of an idea of just trying to control as much as you can and not leaving anything to chance. But generally speaking, the people that are doing these experiments, they are using some type of sample mask.
Okay, and if you don't use a sample mask, you should change the area in your setup window?
Yes, you certainly should do that, and that's either going to be based on the size of diameter of this O-ring that we're using, or whatever cell you're using, what the exposed surface area is. But that makes it real easy with the sample mask because you know what that exposed area is.
Okay, thank you.
Let's see, where are we at relative to OCP? So here's another neat thing. You can kind of monitor what we see going on here. So our scan started at about 500 millivolts here. It's probably getting pretty close to being done, and man, we have a lot of current going through here. It's awfully corrosive, so I'm interested to see what's going to happen. Let's see if I can. Excuse me 1 second. These things are popping up on me. All right, here we go. So our open circuit was right here at 486. Like I said, we scanned about 15 millivolts on either side, and it looks like it's finished. So here we are, just above minus 500 millivolts. So here would be 486, and as we come around here, look, at 46, we're very close to zero current. So all of these are just good indicators to kind of take mind of, and then from 46, we'd go down to about 470. So we're definitely scanning over the window that we defined, and at 486, our open circuit, we're very close to 0 amps. So that's just a good indicator that we probably collected some pretty good data. Obviously, visually, just looking at this is not linear, but if we just isolate right in here, we have somewhat of a linear response. It's on either side of 0 amps. So this is what we're going to do here in a little bit. We're going to take this bit of data right here, and we're going to model it and see what kind of values we get for an RP value. So let me see here. We're going to go ahead and put that to bed, and let's open up Analyst. And the last experiment I ran is going to pop up right here. So let's go ahead and open that up. Here's the data that we just took. And what I'm going to do is I don't want to try to call this whole set of data linear and model after it. There'll be a lot of error involved with that. But if I just select a smaller portion, and I'm going to do it somewhat evenly, both on the both with respect to how many millivolts I'm taking here, or the amount of current on either side. But I'm going to just kind of model this little bit of data right here, and we're going to call that linear and see what kind of values we get spit out. So model it right there. We're going to isolate that. We're going to come up here to the polarization resistance. So I'll back up. In our software, depending on the experiment you ran, you're going to see a different set of options at the top here for things, excuse me, different things you can perform to the data. So for the polarization resistance experiment, you're going to get the tab and polarization resistance. So we're going to click on that. It still has the values that we set up at the beginning for the density and the equivalent weight. It's asking you if you want to change your TOEFL values. I'm just going to leave them the way they are, and I'm going to click calculate. And right down here, you see a corrosion rate, 26. That is kind of high, but it's a demonstration. So here are the detailed values. Now, let me just copy these and put these into Excel so you can see what I'm looking at here. Okay, so right here, this value was our open circuit potential. These were the limits that we scanned over for the whole experiment. These were the TOEFL constants that we used. Our RP value is a very low 450 ohms. Our steel is corroding very, very fast. I honestly expected something to be much higher, a couple kilo ohms at least. So we have a very corrosive system. Applying the Stern-Geary equation, we're going to get about 58 microamps as this I-core corrosion current. Our software did all those calculations there for us at a click of the button. When I go and run the EIS experiment, we're just going to calculate these, I guess you could say by hand here in Excel, and see what values you come up with. The big factor is going to be what we get for RP from our modeling data. If it's very close to this value, then the rest of the values are going to be very, very close. If we see a discrepancy between the two, then obviously these values are going to change as well. But first we have to run the experiment and see what results that we get. So what I'm going to do now is back in Gamry framework, this is where we run the experiments from. We go to experiment and potentiostatic EIS. So change this to 3. What we're going to do here is we're going to scan from a frequency of about 10,000 hertz. I'm only going to go down to 1 hertz just to save time. You might want to go to 0.1, as low as 0.01 hertz, depending on how low of a frequency or the data at low frequency you want to get. But just to save time, I'm just going to stop it at 1 hertz, and that should be good enough for what we're doing here. We're going to collect 10 points per decade. We're going to apply just 10 millivolts as our AC signal. Remember back to the previous experiment, we scanned 15 millivolts on either side of open circuit, and we were able to assume that we had a linear, pseudo-linear response to the system. So you can see how the two kind of echo one another in terms of the kind of perturbation we're applying. The other one was direct current. This one is going to be an AC signal. Same thing down here with the initial delay. Everything involves around open circuit. So we're going to take the open circuit measurement for about 10 seconds. I assume it's going to be still nice and stable, and we're going to start our measurements. So let's go ahead and get going on this. So the first thing you're going to see here, again, is our open circuit potential measurement. And as we're going along for about 10 seconds, it's nice and stable. And now we're collecting our data to make things easier. Let's look at the Z-curve. This is going to be the Bode plot. If you'd like, I can switch it to the Nyquids. I will here at some point. But the real data that we're concerned with this EIS scan is going to be on the DCN once we get to lower frequencies. The higher frequency data for this particular experiment just isn't as important, but we'll still model it, and then we'll tease out what our RP value is. So this is the Bode plot you see being produced here. Here's the nice Nyquids curve we see being produced here. So you can see it's producing that classic semicircle shape. I doubt we're going to get all the way down to the x-axis here again. We might even see a little tail formed right here, but let's see what happens. It should be done here in just a few seconds. And if anybody else has any other questions, we could certainly start to address a few now.
Yes, we did have another question. They were asking, if you don't know your TOEFL constants, do we have an experiment that will measure them?
Yes. I mentioned at the beginning of talk that actually doing that would be probably another pretty good demonstration. But very similar to what we did for the LPR experiment and figuring out what the open circuit was and then scanning a very small window, and then we get what we see as a linear response. You could broaden out that experiment and do the Potentio dynamic scan. And essentially what it's going to do is it's going to do the same thing we did for the LPR, but it's just going to be a much larger voltage window. And without getting into too much detail, you can look up the information on how to find these pretty easily. But from that experiment, you can tease out what your TOEFL constants are going to be. And yeah, if you need any help doing that, give us a call. But as I was preparing for this, I was thinking that's probably another good demonstration video, is how to figure out what your TOEFL constants are. Looks like we have this all done. As I said, yeah, we see that little curl happening right there. It's pretty close to getting, let's go ahead and move it to the analyst side here. So I'm going to open up analyst again in our data we just collected here. And yeah, our value is going to be a little bit higher, but it's going to be pretty close to what we got. So a couple different things you could look at here. One, this data point, where it's sitting, that's going to be pretty close to the RP value that we tease out. So this value right here in ohms. Same thing if we look at the Nyquids plot. The distance, I guess, in ohms, the diameter of this semicircle from this point, and as we come across to where it meets the x-axis again, the diameter of this, that's going to be your polarization resistance. That's going to be really close again to our value. When I model this, my guess is this line's going to come down right about here. So it's going to be off a bit from if you took this tail end in, but you'll see here. But those are just some things you can do. If you don't want to model, then you could take those values and they're going to be awfully close to what we get with the models. But well, I guess one thing you should do is kind of scrutinize how good your data actually is before you model it. So one good way to do that is looking at your Kramers-Kronig transformation and see if it lines up with your data. And what you want to see is what we see exactly right here. We want to see this go right through the data. Same thing with the Nyquist. We're seeing it line up right with the data. I could show you some horrible data and this wouldn't line up at all, and you could start throwing out data points or even trashing all the data together. But this is a good indicator that you have good data, is that you have a good fit from this. Let me go ahead and get this off of here. But what we want to do is we want to fit this data. And as I said before, we're going to use the modified Randall cell. I'll show it to you again really quick. Oops, one more down. This cell, this model that you see right here, what you would typically see right here is a capacitor, but I'm going to use a constant phase element, and that should fit the data a little bit better. But the value we're looking for is RP right here. And I guess I should add, here's your solution resistance. This is this represents the resistance and the capacitance seen on the surface of the electrode, the surface of our working electrode, that little 1 centimeter squared surface of steel exposed. So maybe you can visualize that a little bit. You can see that this right here is your solution. This is the surface of your electrode. The solution is purely resistive. On the surface of the electrode, you have your RP value. That's, in this case, that's the impedance or the resistance to the oxidation reaction that's taking place on the surface of the electrode. And then you have this capacitance in parallel. Both these things are occurring on the surface, and your double layer capacitance that forms on the surface. Let's go back to the data here. So I'm going to use that model. And I have one right here, Randall's with the CPE. And so it has some starting values right here. I'm going to auto fit these. And the data doesn't look too bad. So what we're going to do is close this. And you can see I'm a little shallow in the capacitance up here and that curl, but so this is a pretty good fit overall. The Bode data always makes it look a little bit better. If you're a visual person, then you might prefer looking at the Bode fit when you want to fit your data. Like, oh, that looks so much better. But at the end of the day, it's the same either way. So I need to get this thing out of the way. So let me copy these so I can show them to you in Excel. We can see what values we got here. So for this one, I'm showing an RP value of about 700 ohms, giving an error value of about plus or minus 6. So that's definitely a good modeled value. RU and these values I'm not too concerned with. This is the uncompensated resistance. This is related to the constant phase element, but we really don't need to discuss those. But the RP value here about 720. If we go back and, excuse me, look at what we had here. We had 446. So in this span of time, I think my system is still trying to get somewhat equilibrated, and the initial corrosion happening on the surface is probably slowing down ever so much. But still, I expected much higher values compared to what I had yesterday. I can already think of steps I probably could have taken to improve the surface, and I think polishing the surface probably would have helped out. There's a good chance if there's some rigid areas in the area I exposed, then that could cause corrosion to happen quite rapidly. So shame on me for not sample prepping as well as I probably could have. But still, let's go back to these values. So we have the, about 727 is what we have. And we'll see what we end up with. So if we go with this, let's make this a little bit bigger. So based off our RP value of 727, using the same Koffel constants, the default ones that we used, and all the same density and the equivalent weight that we used from previously, we get a corrosion current that's come down to about 35 microamps per centimeter squared. And you know what? I want to try something really quick while we're talking about this. I'm going to run another LPR experiment here. Let's see if things slow down a little bit on here. So while that's running, we can discuss everything else. And then at the end, maybe we can come back and take a look at this. Let's go ahead and let that run. Let's go back to Excel. So from the EIS experiment, we got about 727 ohms that we modeled there. It gives us an I core of about 36. Coming to a corrosion rate of about 16.5 milliinches per year. Those are the units there. I see it cut off a bit, but it's milliinches per year. So that is compared to what we got here of 26 or 27 milliinches per year. But it all goes back to this RP value that we calculated or that we found from the data. So here from the LPR, we got about essentially 450 ohms. So running the EIS experiment, we got about 727 ohms. So would you say there's a discrepancy there because one value seems to be almost twice as much as the other? Depends on what you define as really good data or not. I expected the values based on what I ran yesterday to be closer to about 3 to 5 kilo ohms. So seeing this value right here tells me that the surface that I isolated compared to the surface that I ran yesterday, there's something different. I'm using the same solution, the same setup, same cell. So I'd point to something being different on the surface of the electrode itself. Let's see what's going on with our LPR measurement. So here's something interesting. during the first LPR experiment, the currents were much, much higher than what we're seeing right here. So the currents themselves have come down. That tells me that that initial blast of corrosion that we saw when I first put the cell together is slowing down a bit and reaching what I'll call a point of equilibrium, or maybe steady state's a better term for that. But all little things in experiments that happen. So run multiple experiments, do similar things that I'm looking at right here. Try to figure out what has changed in your system when you see stuff like this, and monitor it the best way you can. But once that's done running, we can go ahead and add another, we'll do another calculation and see if it comes closer to the 727 value we got here. I have a feeling it probably will.
Andrew, when you're back on that, when you're back in framework for a second, we had a question that would be good to show you. How do you decide on what? How do you decide on what the linear portion of the curve is? Honestly,
that's one part of the experiment or the data analysis that's probably going to be dependent on the individual. But what you're looking for at the end of the day is you want a very linear portion of the data. You want to take it relative to what your OCP and 0 amps is. So you don't want to come down to this area and say, well, this looks really straight. Let me take this data right here. Or the same thing for this. Well, this is nice and straight right here. Let me take this data. You want to take data relative to this OCP value that we're looking at, because the RP value you're looking for is just a way for you to get that I-core value. You cannot measure I-core directly. There's no technique to do that. And some people would say, well, if you're measuring the open circuit potential, there's no current flowing right there. Should I-core be 0 amps? That's not the case. That's something that just, it can't be measured with a potentiostat. But what you can do by use of the Stern-Geary equation, having accurate Toffel constants, is figure out what this corrosion current is relative to the OCP value. If anybody remembers some of their more advanced mathematical techniques, it kind of comes back to perturbation theory. So a small perturbation, let it come back to its steady state, and then try to figure out what the constants or values are relative to that steady state. It's similar to that in a way. At least that's the way that I reasoned it out myself when I was learning this. But when we take this data, let's go ahead and do this. Let me show you what the difference will be. So this experiment's done running. Let's go ahead and open up an analyst. Let me get this thing out of the way again. So we're gonna sample this in different regions and see what the different values are gonna be. So first, I'm gonna do what I was looking for. So I'm gonna select a value that's relative here to the 0 amps, and I'm gonna take about the same amount of data points on either side of it. And again, I want to scrutinize that it's linear, so I'm gonna come right about here. And then the same over here. Another way you can look at this is how many millivolts you want to take relative to your OCP value, which, if we go back, we were sitting here at 493. So this shift that you see here, this is 493.5, 0.5, 0.6. This is very stable. We're essentially at 493. So at the 493 value, which we're going to have somewhere close to about right here, I'm taking the same amount of data points on either side of that, because this is my area of interest in the system, is what's going on right there. So I'm going to take either points of that, go to polarization resistance, get the Toffel plots. Look at my corrosion rate. It's come down to 13 relative to what it was before. And my RP value, let me copy these again so you can see them all. Am I on the... So my RP value has come down to 900. Remember, with the modeling, we were up at 727. Here we're looking at 900. Comes to an I-core of 28 relative to the, oops, sorry, I'm on the wrong page. So 727 gave me a corrosion rate 35.88. gave me an I core value of 36, the corrosion rates about 16, 17 millinches per year. If we look at the LPR, we have RP at 900, I core at 29, corrosion rate at 13 millinches per year. So you can see we're starting to converge on the same value here. Just need to give the system a little bit of time. But what if I was just to choose different values here? Let me get rid of this line. What if instead I decided that I wanted to go from this point to this point, because that just looks nice and straight. That's just what I want to choose for whatever reason. So now I'm going to calculate it out. Now our corrosion rate's up at 28. The values that we have, back down to what we just saw before. Let me copy these and put them into Excel for you. Based off that line that I just placed, I'm at 423 ohms for my RP value. But I would say that would be a very bad choice because one, look at the slope that you have there relative to the slope that I produced earlier. Let me show you both lines. There's your difference. So what you're aiming for is something similar to the first line here that we modeled with, but everybody, depending on just a few different points, it's going to tease that line a little bit. Run multiple experiments. That's how you're going to eliminate the human error involved with that more than anything else. But yeah, it's something that comes with experience, I guess you could say. But there's some key factors that'll limit just how much you could change what you decide is linear or not for the LPR measurement.
Okay, Andrew, can I jump in for a second?
Yeah.
To everybody, there's a lot of questions incoming to me, and there's no way I can keep up with them, nor could I ask them all to Andrew. So remember, Jacob and David are also co-hosts, and they can help answer questions also. So if some of you could also direct questions to either one of them, that would be greatly appreciated. We did have somebody who wanted to ask a question. I don't know if Mohammed is ready to ask his question, Mohammed Afifi. But I could unmute you and you could ask your question at this time if you wanted to, Mohammed.
Hello, everybody. Good morning.
Morning.
Are you hearing me now?
Yep.
Yes, we can hear you loudly.
Yeah. Hi, Dr. David. Hi, Andrew. Nice presentation, nice demo. I would like to check with you if, as far as I know, that the sequence of the experiment is very important. And I learned from Dr. David a long time back that we have to start with non-destructive experiment and then destructive experiment. So when we start in destructive experiment like polarization resistance and then go to the non-destructive experiments like impedance. So do you think it will affect on the final result, or it's not necessary?
I would defer if I assume you're referring to Dave Loveday, who's one of the co-hosts here. I would defer to him, but in terms of the specific order you would prefer, because he's a corrosion expert. I'm probably more of a novice, definitely more of a novice compared to him. But one thing that I would point out, when you say LPR is destructive relative to EIS being destructive, if you ran LPR constantly on the same sample over and over again, then yes, you're eventually going to corrode the system. But if we're only applying 15 millivolts on either side of OCP for just a minute or two, then, as I said before, it's an active experiment. You're perturbing the system, but I wouldn't say that it is, fully destructive. It's kind of, I guess, in a gray area. For example, if we were to compare the Potentio dynamic scan that I mentioned before, where we're scanning over voltage range, 1-2 volts, as opposed to just a few milliamps, that is destructive, and you certainly are going to change the surface of the material. But the LPR, I don't see as a truly destructive technique as opposed to a lot of the other experiments where you vigorously polarize the surface as opposed to just enough that you can get a measurement. And if you think about what you do with EIS, once you get to the DC side of an impedance measurement, then essentially what you're doing is applying the same perturbation as you were with the LPR experiment. Now, me only going down to 1 Hertz, that certainly isn't polarizing the surface as long as the LPR experiment was. But if I start going down to 0.1 Hertz, 0.01 Hertz and collecting data, then that's polarizing the electrode just as much as the LPR experiment was. So if in the LPR experiment you feel that you're actively modifying, destroying the surface, then it's probably not much different than a really low frequency EIS measurement. But it's kind of a gray area. Potentiodynamic scan, where you're going 1 or 2 volts, you certainly are modifying the surface, but that's what you're trying to do. You're trying to pull out information due to that. In an LPR experiment, you don't want to cause a vast change in the material. You just want to perturb the system enough so you can figure out what that I core value is. So it's a very small perturbation just so you can tease out what that RP value is to get the I core. So is LPR destructive? It's certainly active. There's no doubt about that, but I can't say for sure I would call it a truly destructive technique. But you certainly can see corrosion from the system. There's no doubt about that. So the system is changing. But depending on your specific system, you could see things quite differently. It depends on your substrate and your solution as to how your system is reacting to such an experiment.
Okay, that's fine. That's fine. Good.
Yeah.
Thank you.
Yes, you're welcome. Any other questions in particular that aren't too terribly specific?
Yeah, I'm dealing with a bunch of.
Yeah, you get a lot of very specific experiments that questions that are difficult to answer in a form like this.
Yes, I do want to make a note though, because I've had a couple people ask about this. In the setup window, Andrew, can you pull the setup window again for, say, LPR?
Well, here's one, but we can. Yeah, this is all the information.
Right there. Okay, so in the middle of this setup window is equivalent weight. A couple of people have asked about calculating that. There are online calculators to calculate equivalent weight, but you need to know the composition of your alloy.
Yes. Yes, that's correct. If it's a pure material, that's very simple. But if it's going to be a composition of titanium, you have some kind of aluminum in there, something to that degree, then yeah, you'll have to know what those are. Something else, even since you brought it up, a good point is if you have an alloy like that composed of different materials, when you run experiments like this, you really have to think about what is actually corroding. You might have, is it the aluminum in it? Is it titanium? Is it something else? So that's something to take a lot of consideration in. Is if you make the assumption that it's a uniform surface and everything's corroding at the same time, you're selling yourself a little bit short. You definitely want to take a look at what material that the alloy or your mixture is composed of is actually contributing most to the corrosion. And maybe they are all equal, but you still should scrutinize that.
Right.
There's a couple different ways you could get to that answer.
Okay. We have another question. We're going to unmute Ali, Ali Musavi. Okay, Ali, can you ask your question now?
Yes. Do you hear me?
Yeah.
You have to turn it off to your speaker. Where's the microphone? You echoed really bad.
Okay, it's better now.
Let me mute myself.
Should be better now, right?
Yes.
Do you? Oh, I don't have them. Do you have me?
Yes, I can hear you. Can you hear me?
Hi, sorry for the confusion. Two quick questions now that we talk about the equivalent weight. If you can send that particular, if there is a website that you can give the composition and it gives you the equivalent weight, that would be perfect. And my question was about a fluctuation in the data. We were just right now that you were doing LPR, Andrew. We were doing the same on an internal sample at 500 C. It's a high temperature environment that we are doing the test. The OCP is fairly smooth. Only we have 10 millivolts change in 60 seconds, but the linear scan has a lot of fluctuation. I mean, actually the data is unusable. So my question particularly would be, what is the cause for all these scattering fluctuations? And so far we couldn't find why we have so much fluctuation.
Couple different things. One, have you run the experiment just at room temperature instead of 500 C and got good results?
500 degrees. What was your test in room temperature? Was it good?
Okay. No, actually that is, we did it at room temperature. The
And
salt
it
I
worked?
didn't do. Salts,
Well, yeah,
Them is that
Molten salt.
we have a molten salt, so we cannot run it on room temperature is solid. The solution
Yeah.
that we do the test on,
yeah, your name's very familiar. I think we've emailed a couple times before, right?
Yeah,
I think
we
you're an academic institution. I think it's Virginia Tech, aren't you?
right,
Did I
right.
get that wrong? Okay, I thought so. Yeah, so your specific question, contact us later. We'll take a look at your data and see what it is. But one thing is that you're at very high temperatures. You're in a molten salt. Your substrate material might, due to thermal issues and due to just the nature of the molten salt, might not leave the system stable enough to make the measurement. But yeah, the one thing would be, well, since you're a molten salt, you can't really do a room temperature measurement, I don't think, right?
Yeah,
So
it would be solid state.
yeah, we'd have to talk about it a little bit more. The one thing I would have said is, what does the OCP look like? But send it along. We'll take a look at it and see if there's something that stands out to us. Yeah, I don't have much experience in molten salt, but we certainly know some other people, and I think a couple people at Gamry at least are probably a little more knowledgeable with molten salt and experiments in there. So we might be able to help you out a little bit with that.
Thank you.
Yeah, send over the data and let us take a look at it. Maybe even some photos of your setup and things like that. Yeah, there could be a lot of different things. Since you're at such a high temperature, I also know that you aren't using our cell cables. You have to be adding something on to get to the cell itself. So there might be an issue there.
Yeah.
So all those are things I guess we'd have to kind of take a glance at. But yeah, send us over the data. We'll take a look at it.
Perfect. Thank you.
Yep. Any other questions about anything? Let's see what happens. Do I still have everything hooked up?
Yeah, Andrew, you've mentioned Potentio dynamic scan a couple of times. Could you just give a brief overview of what that is?
For the Potentio dynamic scan here, this experiment you'd end up running. I just want to show you this because it looks just like the LPR experiment setup window. You have a starting value of potential you're going to scan from. Let me put it, these are the default values. So the default values here are scanning at 500 millivolts. It's starting at negative 500 millivolts as opposed to the minus 10 we were looking at versus EOC. Final is 1.5 volts versus EOC compared to just the other 10 millivolts that we were talking about. So this is definitely going to be nonlinear. Scan rate right here is still the same. You want a fairly slow scan. You don't want to have a fast scan for this. And then the three key pieces of information, the area, the density, the equivalent weight right here are required. So in terms of what you're actually doing at the experiment, it's not much different than LPR. You're just scanning over a wider voltage window. And I don't know if I have a picture. This was an older talk. It's not going to be in here. And I should have added a picture of what a TOEFL plot will look like. So you're going to get a TOEFL plot, and in these different regions, you're going to see passive and active regions, and you can what you can do is plotting your the voltage versus the current. It's hard to describe what it's going to look like. You'll, based off the information you're going to get, you're going to be able to get your TOEFL constants. You can actually get the I-core value as well. Again, you're going to have to do some extrapolation of the data as it's not linear, but you can find linear regions from it. Yeah, I think that question kind of solidifies we should do another talk like this, creating TOEFL plots and how to pull out what those values are. I can say that if you go to our website, or if you just kind of do a Google search for Potentio dynamic or TOEFL plots, creating TOEFL plots, you're going to find a lot of information on them, and you'll see the images related to those of what the plot's going to look like. You can plot them a couple different ways, but yeah, that's kind of the information you can pull out. I'll have to set up another talk to really go through what that is. It's fairly detailed, and I don't want to walk through every last step. We'd be here probably another hour if we did that, which is another good talk. So if you want to give us a call for us to show you what that is and how to run it on the Potentiostat and how to make your calculations and things like that, then just send us an email or give us a call. We can show you what to do. But I have a feeling that's probably going to be the next demo that we do is doing TOEFL plots and pulling out the constants and the other information you can get out of that.
I would probably agree, Andrew. We have a lot of questions on TOEFL constants and TOEFL plots.
Yeah,
that we haven't gotten to, so a lot of questions.
Yeah, so provide your email address with your questions, and we can put together something, point you in the right direction, or probably do another video like this or webinar like this talking about how to create those plots for you.
Okay. Yeah, just let me back that up. If you've asked a question and we haven't been able to answer it, please make sure that you put your email in chat. We're saving the chat, and then we will follow up separately later today or tomorrow or over the next couple of days as we can get to it to answer your questions then. So, are you done there, Andrew?
If nobody else has any other questions, then yeah, I'm pretty well all done with everything I was going to show.
Okay.
Yeah, I'm not.
That's fine. So as far as the demo goes, there's still, we are, like I said, we are saving the chat, and so we'll be able to answer the questions that have come in. You know, and then we'll be sure to follow up with people as long as they provide us with their email address.
Yeah, you can always send us an email to sales@gamry.com if you have a question like this. That's another way to get in touch with us if you want to ask a question directly that way. But yeah, at this point, I think I guess we're just about all done for today. And I guess the audience has decided the next demo is going to be a TOEFL demonstration. Yeah. That makes life easy. We're always asking for new ideas for doing these webinars, so that's one way to do it. Ask a lot of questions about a specific topic, and then we'll do a webinar on it.
Okay. Yeah. Okay. I think everybody, we're going to stop there, and then We will be sending out a link to the recording in tomorrow's Friday Focus email, so you can watch it again, or you'll have a video to see how to set this particular cell up. And as always, watch those emails, because we're going to announce more webinars very shortly. And we hope to see you at the next one. Thank you, everybody. All right. Have a nice weekend.